Hello and welcome. My name is Florian Lehmann and I'm going to present you the work Heartbeats in the Wild, a field study exploring ECG biometrics in everyday life. I have worked on this topic together with my colleague Daniel Buschek. We are both from the University of Bayreuth. We have explored whether it's possible to distinguish people based on heartbeats. For this, we ran a field study and recorded the heart activity with a chest belt tracking device from 20 participants over one complete week. The technology to do so has already arrived in the consumer market. For instance, as you can see in the picture, the Apple Watch Series 4 can be used to measure the ECG, and this is mainly done for health applications. But pioneering related work by Biel and colleagues and Chiyoso and Uchiyama showed that the ECG can be used as a biometric. Chiyoso and Uchiyama have motivated their work with an use case in telemedicine where sensitive health data is stored and needs special protection. This is interesting since the health data can be used to protect itself. For instance, the electrocardiogram or short ECG can be used for that. But how does the ECG look like and which information does it contain? Here you can see a schema of the heart, it's on the left. And on the right you can see an example of an ECG line graph. I'm going to describe you briefly how the ECG reflects the heart activity. A heartbeat starts at the sinoatrial node, short SA node. This is the pacemaker of the heart. An electrical signal spreads from there and follows the nerve branches which are colored blue. The signal stimulates the cells and makes the muscles contract. First, the atria contract, which is reflected by the P wave. Then the ventricles contract, which is reflected by the QRS complex. That is the most prominent part of the ECG. The T wave then indicates when the heart went back to the default or resting state. After that, the complete procedure kicks off again. You can find more details on that in the paper. But basically, this is the information which can be used to identify a person since it's specific for each person, at least to some extent. Other prior research relied mainly on lab studies or on data from public medical databases. This is why Singh and Singh called for field studies. And there was already a field study by Ye and colleagues, but only with 5 participants. With our study, we wanted to fill this gap and investigated the ECG as a biometric in everyday life. In addition to that, we collected touch data and wanted to look at the ECG whether it can be used to indicate mental stress. But for this work, we concentrated on the ECG biometrics part. In our study, we had 20 participants, of which were 9 female and 11 male. The ages ranged from 18 to 34. Overall, we collected the data for 1 week. The field recordings were covered by 2 lab sessions. Here you can see an overview of the study procedure. You can read it from the left to right and within sessions from top to bottom. Important parts are highlighted blue. The ECG recording started right after the briefing in lab session 1 and ended before the questionnaires in session 2. We recorded the ECG for 1 complete week. We obtained the signals from the participants with a MovieSense chest belt tracking device. The chest belt had dry electrodes embedded, and in total we used 9 sensors, of which one was a ECG Move version 4. Both versions are the same according to the manufacturer. The only difference is in battery life, and the version 4 is water resistant. In total, we collected 36 gigabytes of raw tracking data. On that data, we ran a pre-processing pipeline. This contained basic methods, for instance, downsampling, filtering, and a R-peak detection. You will find details on that in the paper. For now, we are going to skip the details and continue directly with the model. That's the model we use for evaluation. For each P&Q in the data, which are user and attacker, we trained a classifier. We fed data from the user and rest of the world to it. An user was labeled as 1 and the rest of the world as zeros. Attacker data was spared out from the training data. In the testing phase, we fed data from the user and attacker to the classifier. They should be recognized as a 1 or 0. With this model, we tested 2 scenarios. In scenario 1, which was a random subsampling approach, we ignored the order of cardiac cycles and days. For training, we used 4,000 samples for both user and rest of the world. For testing, we used 1,000 samples for both user and attacker. In scenario 2, we kept the order of cardiac cycles and days. This might be the more realistic case. Scenario 2 was divided into 3 variants. In scenario 2a, we used data only from day 2 for training, since this was the first complete day of recordings for all participants. In scenario 2b and c, we shifted the border between enrollment and validation. We subsequently moved 1 additional day to the training set, which were day 3 and day 4. In scenario 2a, we had to halve training and test sample size, since some participants had fragmented data sets. Now, which classifiers did we use for the evaluation? We used 3 classifiers for evaluation: a random forest classifier, a support vector machine, and a neural net with noted parameters you can see on the right. We optimized features by computing a correlation matrix and used an extra tree classifier. This way, we identified the min, max, and mean of the QR, RS, and QS intervals as the most promising. And now I'm going to present you the results. For evaluation, we plotted the true positive rate against the false positive rate. This way, we got the receiver operating characteristic curve and derived the area under curve from it. The more the curve sticks to the top left, the better the classification works and the area under curve increases. We also computed the equal error rate, which signals when the rate of correct and wrong classifications are the same. The lower the rate is, the better the classification works. In particular, we made decisions on 3 subsequent heartbeats. On the left, you can see the curves for scenario 1, on the right for scenario 2. Both figures show that the random forest classifier and the neural net work better than the support vector machine. Let's look at the difference between the scenarios in detail. Here you can see a comparison of the random forest classifier between scenario 1 and 2a. The equal error rate in scenario 1 is 5.23% lower than in scenario 2a. We contribute this mainly to the fact that the ECG might differ to some degree from day to day and from situation to situation. And training data from only one day might not reflect this sufficiently. For example, when analyzing scenario 2b and 2c, we found that taking into account data from one more day reduced the equal error rate by approximately 1% accordingly. Because of this, we suggest that a real-world system should retrain dynamically on a daily basis, since the ECG seems to be less permanent. And now let's have a look on how it improves with taking into account more decisions. Taking into account 15 heartbeats for validation, we were able to improve the classification. the equal error rate dropped by 7.53%. We can say making the validation longer can improve the classification overall. In comparison to lab studies, for example to one by Choi and colleagues, our system still needs some improvement. Choi and colleagues reported an almost perfect classification, but they recorded the data under controlled conditions and most likely had less variation in data. We conclude that ECG biometrics work generally in the wild, but not as good as under controlled conditions. Now, how do users think about ECG biometrics? We asked the participants in question 1 how much they agree on the comfort of their chest belt tracker, and in question 2 we asked them how much they agree on wearing an ECG tracking device for ECG biometrics. The results of question 1 clearly show that the chest belt tracker was perceived as neutral. Other ways to record the ECG might be preferred. But even more interesting were the answers on question 2. Over the half disagreed to accept to wear a tracker for ECG biometrics. We interpret this as an aversion to ECG biometrics. So what do we suggest for systems using ECG biometrics? Based on our findings, we argue that ECG biometric systems should be trained adaptively on several days. Otherwise, it might lack of variability in data. The ECG is still less accurate than fingerprints, but could be a promising factor for multi-factor authentication. And since our signals were quite noisy, we see the need to improve how the measurement is done. For example, a chest belt could provide an array of electrodes. The tracker software could then decide for the electrodes with the best signal or compute a mean signal out of it. But we don't want to concentrate only on the technology. That is why we also present reflections on privacy. Especially because ECG biometrics work in everyday life. And the technology is already there, for example with the Apple Watch Series 4 or devices such as the NIME, a wristband device which captures the fingerprint plus the ECG. This is used mainly for authentication in enterprise scenarios. It must be remembered that the ECG does not only hold information about the identity, but also about the health state. We think health data is sensitive data and deserves special protection. In case of a data breach, your identity and your health state would be leaked to the public. So when building an ECG biometric system, it should be at least considered where we want to store and process the data. We think raw data should not be stored on a backend server. Instead, features should be computed locally and data should only be saved for a small period of time. We conclude that it's possible to distinguish people by their heartbeats in everyday life. We see the need for future studies to go beyond lab studies and to evaluate ECG biometric systems in the intended application context. Finally, we think privacy is an important part when designing ECG biometric systems and should always be done responsibly. We are happy to share our code and refer to the webpage you can see here. You can go to the website by simply scanning the QR code and you will find more information on how to get access to the code. Thank you for watching.